All right, so welcome back. I want to do a little bit of a follow-up to yesterday. So yesterday, if you remember, we covered conversions and translations between units. How do you go from mmHg to torr to atmospheres to Pascal, from Fahrenheit to Kelvin, and all these other things. And that's going to be mathematically a background that we need to do the rest of this unit. Well, today I want to talk about the other half, which is the chemistry ideas. How do we use what we're learning right now and get ready to understand these different laws? Because what we're going to do this chapter is talk about, 5, 6 different laws that help us understand how gases work. If that doesn't sound quite like chemistry, it's because we haven't worked with gases much this year. I mean, we said, okay, they have more energy in some way than a liquid and less than a plasma, and we'll get to them later. Well, here's later. So today I'm going to go ahead and shrink me down because I'm less interesting than what's behind me. I want to talk about the kinetic molecular theory. Now, your sub should have given you a note sheet, and I am going to collect that on Monday along with the unit conversion sheet you have as homework yesterday. By the way, if you're not done with the unit conversion sheet, don't panic. I'll give you some time at the end of this after the video, which you can work on the unit conversion sheet, as I said, on my homework. That being said, this is your summary of this, so if you don't want to go back and watch this video right before the final or the test, it probably behooves you to actually do these notes, get the easy completion points for them anyway, and have a one-page summary of what I talked about. And I'll try to highlight it and say, okay, look here, write it down. Let me help you get this out of it. If you need to pause the video, go back, move over, that's the beauty of a video, but for now I want to go through it. Okay, so today is about kinetic molecular theory. And kinetic molecular theory is a big sounding, scary word for an easy idea, which is really just the underlying concepts that tie all of our other gas laws together. So we have like Amoton's law and Boyle's law and Charles' law and the ideal gas law and the combined gas law and all these other laws. And if I just taught them only, this is honestly an algebra class, and that's not the point. There's some chemistry here, and this is really the foundation that lets us do that algebra in a way which is helpful to our chemistry. So the first thing up here, your first blank, is that kinetic molecular theory describes matter as, it turns out, particles in motion. And all matter, not just gases, all matter is particles in motion. Your body has individual atoms in it which are currently in motion. Your desktop, which is undeniably a solid, still has things moving in it. The air in this room is racing around this room in some ways, as are the sound waves, as are the photons from light. Literally anything is matter in motion. There's no such thing as not in motion. There's very small motion, but it's in motion. So we're clear. The first blank here, matter as particles in motion. Now, in our case, we're going to describe that matter as small, separated from one another by empty space. And I've disappeared from you here. Let me fix that. Now, small particles separated by empty space. And we're not talking like, oh, small particle here, small particle. No, we're talking like big empty space. We're talking small on the scale of atoms and empty spaces on the scale of lots and lots and lots of atoms. It's not like they're right next to each other. They're almost there. That's a liquid. They're really quite far apart. And that's really helpful when we start talking about gases, because it's going to help us distinguish them from liquids and solids. This means that gases are very different than solids and liquids. So over here, gas particles are small, separated by large spaces. This is very different than solids and liquids, which are close together. That's really what it is. We'll talk about that bottom point that I'm kind of covering up with my face right now later on. As we move along, though, I want to talk about particle motion, because I think it's kind of interesting. Okay, now, gas particles are in a constant random motion, and that's mostly true. And I ask you on your sheet to write down that they're always moving in straight lines, which doesn't make sense until you take physics. And they move in a straight line until they collide with something. So gas particles move in straight lines until they collide with, in this case, another molecule or the walls of the container. So over here, there's a little GIF, right, of different things moving around. I want you to kind of focus in on one thing. Maybe choose one red particle and trace it. And watch its motion. You'll see it looks chaotic from a distance, but when, let's trace this one right here. You can see it's moving in a straight line until it collides, and I'm not even going to pretend to keep following it because apparently I'm very bad at that. Whatever. And you can see there is chaos, but only insofar as it's just hitting things and moving around. And that's really not too terrible, because there's only two options. You can hit the wall or you can hit another chemical. Okay? Now, that's nice, Because what we're modeling here is an idea in physics which is called an elastic collision. You can kind of think of them as like bouncy balls that are like elastic balls, boing, boing, and bouncing around. Okay, cool. So gas collisions are elastic, and that means that they don't change kinetic energy or temperature, which means really the particle before the collision and after the collision are effectively the same. All that changes the direction and the velocity, which is kind of cool. If you look, it's not like particles are getting bigger or smaller. They're not splitting or combining. They're just kind of bouncing around. Think of it like marbles in a tray. Is a really good analogy. Well, if that's the case, this constant random motion, that's really going to dictate how we think about gases, because if they're not in motion, they're no longer a gas. So make sure you have it down again. Gas particles move in straight lines until they collide with the walls or each other, and they're elastic, which means no Ke or temperature loss. Okay. That being said, the mass and the velocity do matter. And so that's what determines our kinetic energy. Once you get to physics, you'll see the equations 1/2 mv squared. I don't care about that right now. The m and the v change things. If I don't have a mass and a velocity, I don't have energy. Now, if I have all the same chemical and they're all moving around, the only thing I can change is v. If I mix up different things, I can change both things. But it's not like I can have a particle of helium going along, all of a sudden the helium is getting lighter and lighter. I mean, that would mean it's shedding protons or neutrons, and that's no good. That doesn't happen. It's not like it's getting heavier. It's not like the helium's coming along and just capturing protons and turning into, no, that's no longer helium. The only thing I can really change is the energy, the speed, and the direction. And that's where kinetic molecular theory starts. So again, the kinetic energy is determined by mass. The kinetic energy is determined by velocity. There's not a lot to write down on this slide. What I want to talk about is what's going on here. Can we remember density is mass over volume, right? M over V, one of the very first formulas you saw in science, including this class. And I've done a little back of the envelope calculation here. Basically, I've taken the most dense metal and a relatively normal gas and hydrogen, right? Osmium over here, hydrogen over here. And I've done some just back of the envelope calculations here for the density of hydrogen gas at basically, well, room temperature more or less, and on Earth, and metal at room temperature at Earth. And you'll see the metal actually has about 250,000 times more atoms per area, well, more grams, but the atoms are organized corollary, than the hydrogen does. That's crazy. That's a massive difference. Think about like the entire population of like Omaha, Nebraska, versus one person, or should you want to compare it a different way, like the population of Kansas City versus your family, like massively different. And this really shows up, if I think about it, in this picture over here. So let's say I've got a bubble, like I'm boiling some water in a beaker, like pictured here. Okay, the water is effectively a wall, and the gas is just bouncing around with massive holes in between. And I want to point out how different a gas really is. This animation up here is really quite wonderful for showing you what's going on. You can see just how much less material there is per unit volume, and so it's very low density. And again, there's nothing to write down here. I just want you to realize that gases are more different than you think. Solids and liquids are much more similar than a gas is to a solid. Okay. This is already drawn for you, so you don't have to do anything. You just have to pay some attention to it. I've got a solid, a liquid, and a gas. We're familiar with them. A solid is rigid. A liquid takes the shape of its container, but it's a constant volume. A gas takes the shape of its container, has an indeterminate volume. We've talked about this. What I want to point out here is the solid has very little motion. Basically, they're so tight in that all they can do is sit here and vibrate in their own little shells. And as I warm it up, they vibrate more and more until they shake themselves apart and turn to a liquid. A liquid will have some velocities. It will move around. If you doubt that, take a bucket of water and drop some food coloring in, and over time the food coloring is going to spread out. Obviously, there's motion. I'm kind of lying to you here. You could have a perfectly still glass of water. It would still spread out, but ignore me. The gas, it's spreading out quite a bit faster. And what I want you to notice is the gas and liquid aren't that different in this drawing. Now, remember, the gas and liquid are radically different over here, right? But they're not that different in this drawing. It's just the gas has more velocity. So basically all I'm doing is as I heat it, let's like put some fire under here. All I'm doing is making these things vibrate until I shake loose and they make a liquid. I'm heating these up and they come so much and they shake loose again. Right? I'm just adding kinetic energy. I'm just adding velocity. So obviously the speed, the kinetic energy of a molecule is akin more or less to its state of matter, its kinetic energy. And so if I know something about the energy, I also know something about the motion of the molecule. And that's really the heart of this kinetic molecular theory. And that's what we care about it, which may seem really obvious, but it wasn't. It took a long time to learn this, mainly because we couldn't see things this small for a long time. What this means is this solid has the lowest kinetic energy and the gas has the greatest kinetic energy. So go ahead and write that down. And that's really quite different. Solids low energy, gas is high. Now theoretically I could get even more speed by ionizing this and making it a plasma, although a plasma isn't, I mean it is a state of matter, but it's not something we're going to care about in this chapter. We're not going to do any like plasma rules. That would be crazy, crazy, crazy complicated. Okay, because there's so much space in between gases, I can kind of squeeze that air down and get rid of some of the spaces by pushing the particles closer together. If I expand it, I can make the container bigger and it's going to fill it up, right? And that's really different than a solid or a liquid. Okay, look, I have my solid here. Even if I press on it really hard, it's hard. It's like I can't deform it, right? It's the shape of the solid is the solid. Or if I had water in a container, like let's say I fill this up with some water right now. Yeah, magic water. Now, let's say I stick my fingers in here. Oh, the water overflows. That's because my fingers are displacing a volume. It's not compressible is the word. Now, if I do that with a gas, it's not like my fingers are pushing gas out. I mean, I can actually squeeze this down and compress the gas. This is how your car's engine works. This is how like an air compressor works. There's a lot of things that use this, and this is different than a solid or liquid. We call this being compressible. And that actually does change things. Compressibility of a gas is a really useful thing. So like when you go to the store and you get a soda out of a soda fountain, you know, it's not like they have a giant balloon of carbon dioxide in the back and they're like squeezing it down to put it in your soda. They have a little tank that weighs like 150 pounds that's like at 4,000 psi of carbon dioxide. It's crazy. And nice and useful. I mean, it would be very unfortunate to have to like use the volume of CO2 that a soda requires every time someone filled up. QuickTrip wouldn't have anything else in it. So it is useful. And if you've ever worked in like a machine shop, like I'm doing robotics right now, you'll hear a lot of compressed air because it's very powerful. This property of gases is very useful. Just as the fact that like liquids are incompressible, can't be compressed, is actually very useful for things like hydraulics and pipes and things like that. So they have their own properties, but being compressible is a very distinct thing that only gases really are. I mean, liquids are, you can compress them a tiny bit, but not really. And plasmas are such a different animal, like you wouldn't want to try to compress them. And so really the fact that it's compressible is kind of unique to a gas. Another couple things that are weird to gases is they undergo two processes, diffusion and effusion. So diffusion on the back here is the movement from high to low pressure. Effusion is the movement through a tiny hole, and they're close but different. Okay, so when I hear diffusion, I do hear the word different. Diffuse, different. Okay, it just means that I've got two different concentrations, and so they need to move. Now, on the back, it says high concentration, low concentration, and you'll know I actually wrote from high to low pressure, which are the same thing. I mean, effectively given, you know, same containers and everything. So they're correlated. And one thing you're going to notice is that like concentration and pressure and volume and number of moles and temperature and all these different things combine together. And so you'll hear me using some words interchangeably, just like I use temperature and kinetic energy interchangeably. Regardless, from high to low is what matters for diffusion because there's different pressures, concentrations, however you want to say it. And in infusion, it's a little different. It's just a hole, a very, very tiny hole, like a pinhole, but even smaller. And I want to talk about effusion when we get there, but for now, just write down that effusion, E-F-F-U-S-I-O-N, is the movement of gas particles through a tiny hole. Now, diffusion just works like, let's say I've got this gas that's really under a higher pressure or a high concentration. Like this red gas is in a small area and the orange gas is spread out evenly. The orange gas isn't going to change. It's already happily there. But this red gas being tight together, it doesn't like that. So over time, it's going to move and spread out. Think about it like this. If in my room right now, I walked in with a stink bomb and I set it on my desk, the people close to the stink bomb would smell it before the people in the back. But if I leave it in the room long enough, the whole room is going to smell. That's diffusion. if I light a candle, I might see the smoke right here, and several minutes later, I might smell the smoke if I blow the candle out. Things like that. That's diffusion, just things spreading out. Diffusion is really useful in a lab because it lets us know that over time, a gas particle is going to be uniformly mixed because it will naturally diffuse until it is perfectly mixed. So this is as diffused as possible in the bottom, or close to it. Diffusion also works by a vacuum. Let's say I've got all my molecules on one side and a valve, or stopcock in this case, and a vacuum on the other side, and I open the stopcock and voila, it flows over until it's equal. And it'll flow back and forth until it finds this balance, this point we call equilibrium, and that's what it does. Now that's still diffusion, but this is getting closer to effusion. Okay, so in this little GIF here, I've got green and blue gases. And you'll note if they all start together and I open a valve at the bottom, stuff starts to come out the hole. But the green gases come out faster than the blue gases because they have a smaller radius. So as things are bouncing around in here, right, the green ones are going to find the hole more frequently because they can be off by a little bit more and still make it out than the blue ones. So that means that the smaller gases tend to effuse. Now, I've already drawn you this here. Don't worry about it. You don't have to take any notes on this. But think about it. The smaller the molecule it is, the more easily it escapes through tiny holes. And you've actually experienced this before. Think about party balloons, like latex balloons, and you blow one up with your breath, and it's a balloon, and you go to the store and you get one filled up with helium, so it floats. And a couple of days later, the helium one's all sat on the floor right there with your breath one, unless you're that full of hot air. And so what's the difference? Well, the helium or the hydrogen molecules, God forbid if it's hydrogen, but in some countries it is, are tiny, and the latex is stretched, and it's got a little tiny hole, and it's like, whoop, I'm gone. It effuses. Your breath, it's made of nitrogen and carbon dioxide and water. Well, those are big molecules compared to, let's say, helium. They hit the latex and the hole may be there, but the molecule's bigger, and so it doesn't come out. Now, if you leave the balloon for weeks, it may slowly deflate because, certain holes are slightly bigger, etc. But you can see, like, the gas particle changes. Well, when I'm over here, it's the same thing. Helium being tiny compared to this ethylene oxide, which is big, you can think about it as it hits the pinhole, the smaller one's just going to come through. So smaller gases effuse more than large gases, something we'll actually prove in lab with, like, let's say, ammonium hydroxide and hydrochloric acid is a classic example. I'm not sure which chemicals we'll use this year, but we'll decide when we get there. Okay, the whole point of effusion, the reason why I care about this, is it lets us filter gases one way. This membrane, this pinhole, is really a useful tool. Now, do I really care about that for your test? No, I just need you to know effusion means hole, and that small gases effuse faster. Diffusion means different. Like, those are what I'm going to test you on. But I still think it's interesting this works. Wrapping things up, ideal gases follow some assumptions. And so I want to make sure you write these down. And if there's nothing else you get out of this video today, you need to get this down. This is the big point. Okay. Gases don't take up any space. Yes, that's not perfectly true, but that's our first assumption. A gas particle is infinitely small. 2, there's no intermolecular forces here. Inter, I-N-T-E-R, molecular, M-O-L-E-C-U-L-A-R, forces. Which means that this atom of hydrogen here and this atom of hydrogen here don't know they exist. In real life, that's not exactly true again, but for our assumptions, it's okay. As long as they're not attracted, and it's really useful because if I get rid of this force, the math goes from like easy one-line math to like pages and pages of terrible math. Speaking from someone who's done that math, don't do it, it's terrible. We're going to assume that gases are in constant and random motion. That is true. I can't go with it. And that they're elastic. That's as close to true as we can assume. Now, we already know what elastic collisions mean. We've talked about random motion. Doesn't mean just like whoop, 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 whoop. It means it's going in a straight line and hitting things and bouncing around. But you can't predict it over any real length of time. There's just too many collisions. And the last assumption is that this is true under all conditions of temperature and pressure, which is, of course, not true. If you go far enough into the extremes, things always break. In this particular case, in the labs that we can do, I mean, I don't have a plasma chamber. I don't have several sig fig vacuum. Like, at some point, we're going to be okay. And so these 5 assumptions, no space, no intermolecular forces, constant random motion, elastic collisions, all temperatures and pressure, these are actually really good assumptions. I'm actually going to ask you to know these. Now, most of them make logical sense. If I assume that there are intermolecular attractive forces, I'm obviously going to have to change something. If I assume that gas particles make them shake, I'm going to have to assume they're bigger than just infinitely small, and the math's going to have to change. At some point, it should be kind of obvious why we're doing this. It makes our life clear. That being said, at the bottom of this, it's not true. You don't need to write anything down. This is never actually true. There's certain things that are very close, and they're beautiful. But for the most part, collisions are never elastic. There always are going to be some intermolecular interactions. These molecules are not actually infinitely small pricks. They're all discrete. And so we have to make these assumptions. Now, when you're working with this and you're looking at this and you're saying, Nendik, this is so stupid. Why do I care? These assumptions, when we get around to combining the gas laws, we can say, but I can get rid of this variable and this variable and this variable, and I can make this easy. So look, it's one little sentence. That's just algebra. And that's why I care. You say, well, I could have just looked at those equations. Well, that's not science. That's looking up equations. So hopefully this makes some sense about what kinetic molecular theory is. And again, on Monday, you'll have a quiz open note over what you've done here. So make sure if you need to go pause this and go back to the video and get anything, get all my notes down. Over your notes you took yesterday and some temperature and pressure conversions. Now, you have a worksheet on this. Make sure you're done with that. If you're done with those three things and ready for that quiz, file these things away in your binder. Work quietly on any other homework you may have or whatever else you need to do. Otherwise, I'll see you on Monday. I hope you have a great 3-day weekend. And yeah, see you soon. Bye.